Welcome to the first session on database multi-tenancy in Azure. My name is Paul Burpo. I'm a principal customer engineer on the Azure Fast Track for ISVs team. In this first session, we're going to focus on Azure SQL Database. We will discuss the design considerations and design patterns that you'll use in multi-tenancy database situations. We'll then take a look at some of the features and tooling available to help you implement these patterns, such as elastic pools, sharding, and other tools. First, let's discuss the design considerations for multi-tenant database architectures. You can organize multi-tenant database design considerations into four categories: scale, isolation, complexity, and cost. For scale, we want to understand the number of tenants. If my company has thousands of tenants, it's likely going to result in an architecture that's dramatically different than if I only had 5 tenants. Likewise, you'll also want to understand the storage requirements per tenant and the total storage for all tenants. You'll also need to understand the characteristics of the workload. All of these will help you evaluate the different tenancy models. Isolation is one of the most fundamental considerations, and frequently, the requirements around tenant isolation will drive your design choices and design decisions further down the road. Data isolation is used to separate one tenant's data from another. This is frequently the result of contractual or regulatory and compliance needs. Performance isolation is simply preventing one customer's workload from impacting the performance of another customer's workload. We'll take a more detailed look at the performance isolation in a couple of minutes. Complexity is probably one of the most overlooked design considerations, yet it has a direct long-term impact on the cost to operate your solution and potentially other aspects such as high availability. You'll need to think beyond the simple performance impacts and consider things like, how am I going to implement a schema change after the system is up and running? Does my team have the adequate development skills to build and maintain a solution of this complexity? Or how will I monitor not only the entire system, but at the individual tenant level as well? If you require high availability and disaster recovery beyond the default configuration of the services, what will that look like? Another often overlooked area is tenant customization. How do you allow customization at the data tier in your application? If you do allow it, how will that be implemented? What's the complexity and cost associated with that? And finally, we have cost. In addition to the obvious accounting associated with cost, we can use cost to help us compare different designs and judge the efficiency of a given design. We generally look at the cost per tenant or the tenant density to evaluate various design patterns. Looking more closely at performance isolation, let's consider that we have 7 database workloads running on a single database instance. The blue boxes here represent the amount of system resources each workload is using. What happens when one of our workloads, in this case workload 4, starts consuming more and more system resources? This is known as the noisy neighbor problem. This is a potential problem for almost all database management systems, but it is especially true for multi-tenant systems. One way to deal with this resource consumption skew is to implement a bounding box pattern into your design. This limits the individual workload's consumption of resources to specific limits allotted to them. If a workload starts consuming resources, it will reach the limits of its bounding box, and the system will throttle it or throw an error. This type of error or throttling is known as a transient error in the cloud, and your application is expected to catch this error and then implement retry logic to complete the transaction. So let's take a look at some of the common design patterns used in multi-tenant database architectures. One of the most common architectures we see for multi-tenant solutions is called the stamp pattern. In this model, you deploy an entire application for each tenant, including the application tier and the data tier. Each instance of the application will have a complete database all to itself. This model provides the greatest database isolation, but the isolation requires that sufficient resources be allocated to each database to handle its peak loads. Here, it matters that elastic pools cannot be used for databases deployed in different resource groups or to different subscriptions. This limitation makes this standalone single-tenant app the most expensive solution from an overall database cost perspective. Customization in this model, however, is relatively simple as only a single tenant resides in each database. From a vendor perspective, this also allows you to deploy the solution into a client subscription as opposed to hosting the solution in your own subscription. Management of the database may still be achieved by using SQL logins. Optionally, you can deploy a catalog database hosted in your own subscription to map tenants to database URIs for management purposes. The next deployment pattern is a single multi-tenant database accessed by either single or multi-tenant applications. The scalability in this model can be a bit tricky. The scale overall is quite good, but it comes at the cost of potentially significant noisy neighbor issues. To put it another way, a single customer may be able to consume a lot of resources, giving them good performance. But if customers are competing for resources, then you can run into these types of problems. Generally, this pattern will be used when you favor cost above all else, as you can generally get very high tenant density in this model. Applications that work well in this type of environment would typically have smaller per-tenant workloads to avoid the noisy neighbor workloads. Customization can be very challenging in this type of environment, as the customer's data is typically mixed in the same tables as other customers, making schema and query customizations far more difficult and impactful to database performance overall. Management overhead is generally lower except for disaster recovery scenarios. And what I mean by this is that things like index maintenance, managing backups is relatively easy. But what if one of your customers accidentally deletes some of their data? Are you going to restore the entire database for all of your customers? Probably not. Most likely, you'd either restore the database somewhere else and copy the data back into the production system, or simply not support any type of restore scenario at all for these types of issues. However, high tenant density and low management overhead are where these types of systems shine. A pattern composed of a multi-tenant app and a single database per tenant offers high scalability and strong isolation. The cost can be low to a sort of medium-high depending on the type of workload you have. For example, if each tenant is relatively small and has infrequent spikes in workload, you can take advantage of elastic pools to allow all of the tenant databases to share resources, which will reduce the cost. However, if the tenants have consistent, heavy workloads, then you might not be able to get as much efficiency out of pooling. So in this case, you'd be likely better off not using an elastic pool at all. If you do choose elastic pools, Azure provides tools to help with automation to ease management overhead. Customization in this model will likewise be relatively simple, as each customer has their own database. Using a sharded multi-tenant system is one of the more complex architectures. In this pattern, we scale our data tier out by distributing tenants across multiple databases. We refer to each of the databases as a shard in this model. Typically, a single tenant's data will only reside on a single shard, but there are ways of designing your application to handle multiple shards for a single tenant. This pattern has almost limitless scalability while achieving low relative cost when properly managed. The downside of this architecture is the added complexity involved with creating a sharded system. You may need to move tenants between shards to balance workloads. You may need to split or merge shards to accommodate growth and contraction, or you may need to make data modifications across all the shards. Because of this additional complexity, sharding is probably the least popular option for customers of all those we have discussed so far. We'll talk in a little more detail about sharding and the tools available to assist developers in building and maintaining sharded databases later. It's important to remember that these patterns are not mutually exclusive to each other. It's also possible to mix some of these patterns. If most of your customers are small with light workloads, you might be able to keep them all in a single multi-tenant database, or spread across multiple databases in a pool. Then, let's say you sign a new customer that happens to be a large multinational company. You may want to split that company off on their own database outside of the pool and manage them separately. Many ISV customers also tier their offerings, so the lowest tier may put you in a multi-tenant system with potential noisy neighbor issues, while the higher tiers will be in larger single-tenant models that offer better performance and stronger isolation. So let's discuss elastic pools in a little more detail. In an elastic pool, databases share common compute and storage that is allocated to all the databases in the pool. Databases that are part of an elastic pool are otherwise equivalent to a standard SQL database and still support features such as automated backup, geo-replication, and auto failover groups. Databases can be moved in and out of the pool, and this is generally considered an online operation, except right at the end of the operation when connections are dropped. This loss of connectivity is very brief, typically only a few seconds. Elastic pools help you to avoid over-provisioning based on peak usage of each and every database. Instead, you provision for the peak demand of all databases combined. Likewise, elastic pools allow you to under-provision resources to keep running costs down, at the risk of potential contention issues if multiple databases experience utilization spikes at the same time. While elastic pools are useful for a wide variety of scenarios, they're absolutely ideal for SaaS and multi-tenant workload scenarios. Let's take a quick look at how resource allocation is defined in an elastic pool. You can create an elastic pool using any of the DTU or vCore performance tiers. You'll define several facets of the pool. You'll set the pool settings, and this is the number of DTUs or vCores allocated to the pool and the total amount of storage allocated to the pool. You'll also be able to control the minimum and maximum storage and the minimum and maximum compute of the databases in the pool. Note that this is one setting for all databases, not each individual database in the pool. So let's look at what makes a good pool candidate. Note here that our graph shows DTU provisioning, but vCore provisioning would be similar, except you'd be looking at vCore utilization instead of DTU utilization. So an ideal candidate database would have short, somewhat erratic spikes throughout the day. You can see on this graph of DTU utilization that we have numerous spikes throughout the day, but most of the day the database is idle. This is a potentially good candidate for an elastic pool. And I say potentially because if my other candidates all spiked at the exact same time of day, then I'll need to allocate more resources to accommodate those combined spikes. So now let's add a few more databases to our chart. With only 4 databases, you can already see that if we provision the necessary DTUs for each of the 4 databases individually, it would be a lot more DTUs than we would need if we were running in an elastic pool. So now let's add the rest of our databases to the pool and try and see how many eDTU we would need to accommodate that specific load. We have 20 databases on this chart now, and what we have done is at each point in time on the graph, we've summed the peak usage for all the databases. The value of this peak usage is represented by the black line on the graph. The peak of this black line would be a good starting point for the eDTU of your elastic pool. Now you may actually want to increase or decrease this initial setting based on your goals. So if your goal is cost optimization, then you may want to start a little bit lower. If your goal is performance, then you might want to raise it a little bit. I would caution you that this is just an example, and I would absolutely want to view usage over multiple days and understand any special events that might affect the utilization, such as end-of-month processing or Black Friday events, etc. So now let's take a quick look at a demo where we're going to go over some basics around elastic pools. So we're going to start out in the multi-tenant DB resource group in my Azure subscription. Just a recap, we have elastic pools that are attached to SQL logical servers in Azure. That means that a pool can only have databases that are deployed to that logical SQL server. In my case, I have Contoso Concert Hall, I have Dogwood Dojo, and I have Fabricam Jazz Club. Those are all part of Pool 1 in my Azure environment. I also have a new tenant that I'm looking to onboard, and I've not given it a name. I've just called it new tenant so everybody can kind of track it. So that's the database we're going to ultimately add to this pool. But before we do that, I want to review the pool settings that I've had. Now, what I'm not going to do in this demo is walk through the Azure portal and show you how to deploy an Elastic pool. Basically, you click on Create, and then you search for Elastic Pool, you choose SQL Elastic Pool, and you fill in the information that it's asking for. It's going to ask you for the server, the resource group. It's a very simple service to deploy. I'm not going to walk through it now. It's just very simple. So I'm going to assume that everybody understands how that works. I'm also going to assume that you have some understanding of Azure SQL Database. I might cover some basics here, but for the most part, I'm going to assume that you understand it. So let's click into our pool that we've already deployed. Now, our pool is associated with this tenant, right? So let's click into the pool and see that. You can see that our server name here is associated with that same logical SQL server that we have deployed in Azure. You're going to also see from this overview page that my resource configuration for this Elastic pool is configured to 200 eDTUs. It's a little different than a DTU. It is an eDTU, slightly more expensive, but it's shared amongst all the databases of the pool, so the cost is usually justified if you are a good fit for an Elastic pool. You can also see that I have 3 databases in the pool, and I also have Elastic database settings here configured for 0 to 100 eDTUs. Now, just some quick napkin math here. If I have 3 databases and each database can consume anywhere from 0 to 100 eDTUs, that means that my pool DTU usage maxed out is only 200. That means I can only run 2 databases at 100% utilization. So keep that in mind when you're configuring your pool. What I've configured this pool for is optimal cost efficiency. So I'm hoping and taking a risk that my databases won't consume 100 eDTUs per database in this pool. If they do, I'm going to get throttled. 1 or more of my databases will be throttled. So this is a particular type of configuration. If you want to guarantee that each database can consume all the resources, well, you might as well just deploy each database into its own server and just give it its own 100 DTUs. So different methodologies that you can attack this with. 3 databases, 0 to 100 eDTUs. I can click into each one of these and it will take me directly to that location in the portal where I am looking to configure these. And you can see there are my 3 databases down here. And these settings here are databases that are ready to be added to the pool and databases ready to be removed from the pool. The reason that you don't see anything in there is because I haven't clicked either add databases or remove databases from the pool. So there's nothing that's been prepared for the inevitable save. This is one of those options where you have to save things. Why is it like this? The interface is optimized for managing multiple databases at the same time. So they assume that an administrator may come in here and say, well, I want to remove Contoso and Dogwood. I can remove those from the pool. And now it says database is ready to be removed. So if I click save now, it would remove those databases from the pool. Now, removing or adding a database is basically an online operation, but there is a slight reset when the connections will get reset. And that's when the live migration happens. The database is moved to another host or outside of the pool, you might get a connection reset. If you get a connection reset that impacts you, if you're following best practices for cloud development, you should be using transient fault handling, in which case you'll just reconnect and execute again. I'm not going to save this one out. I'm going to cancel this for now so we can kind of walk through the other settings and see what those look like. So before you get to the individual database settings, you do have the pool settings. Very simple, just like a regular Azure SQL database. You have a slider bar that controls how many DTUs you have assigned to that database, in this case, a pool of databases. And you also have a maximum size for all the databases, so you can keep track of that as well. More interesting is the per database settings. And it's more interesting not because it's complex, but because a lot of customers misunderstand this setting. The per database setting applies to the entire pool, all the databases in the pool. So if you have 100 databases and you have one that you want to be able to consume 1,000 DTUs and everybody else consumes 100, that is not an available configuration option in the Elastic Pool configuration. Okay, so this is a per database setting for the entire pool. Everybody in the pool gets the same setting. If it's something you want to see, it'd be interesting to hear it from you guys. It's a configuration option you want to see. The way customers have been dealing with this over the past 5 years or so is that they create multiple pools with different profiles, or they distribute databases differently depending on customer usage, what they know about the customer. A unicorn customer, for instance, might consume most of the pool most of the time, and then you might have smaller customers that consume almost nothing. You can kind of let them piggyback onto a unicorn. There's lots of different ideas and methodologies for balancing these pools. So this doesn't, in practice, it seems like, wow, it'd be great to have it. But for most customers, they're able to work around that specific configuration by just applying some best practices to, hey, okay, this consumer is too much for this pool. Let me move them to another pool, or better yet, move them out of the pool if they're that intrusive. That's the basics of the pool. So let's walk through adding a customer to an existing pool. So I've got an existing pool. I'm gonna look at my databases and I want to add a customer to the pool. So I click on add databases and you can see I have one database. And the reason it's only showing me one database, I have many databases in this account that are not part of this pool. But this particular database is on the same server. So let's go ahead and click the checkbox. We'll click apply. Now I'm not done yet. So now you'll see that it shows up under ready to be added to the pool. New tenant, ready to be added. Similar to when I looked at removing them, I went and selected some that were ready to be removed. Fabricam Jazz Club. Let's say Jazz is not as popular anymore, so we're going to go ahead and shut that down. So now I've got one database to remove, one to add. If I click on save, it will tell me that the scaling is in progress. So this process takes a couple of minutes. You can see here mine just succeeded. In reality, yours may take a little longer, anywhere from 1 minute to 5-6 minutes. It depends on the scale of the database, the size, a number of other factors. You might get a slight disconnection at the end of the process, but it's not terrible and it's actually pretty reasonable considering the payoff. Once you get databases sorted out in the correct pool, they're usually not moved in and out dynamically. That's not usually a best practice. So it's usually just a trial and error thing for particular tenants in an ISV space like this. Now let's discuss sharding in a little more detail. So what is sharding? Sharding is distributing large amounts of identically structured data across a number of independent databases for performance, scale, or tenant isolation. Sharded databases can be used with a single tenant per database or multiple tenants per database. That's not to say that you can only shard based on a tenant. You define the shard key, and that will determine how your data is distributed across the shards. When developing a sharded database solution, there are some concepts you should understand around shard mapping. First of all, there are two types of shard mapping. A list map, which uses a discrete predefined list. This is typically used for single tenant systems. And a range map, where a range of values is mapped to a shard. Common to both of these models is a shardlet. A shardlet is a group of related rows mapped across tables. So let's take a look at shard map management in a little more detail. Shard map management is handled via the Elastic Database tools. The Elastic Database tools are available for Java and .NET. These tools will create the Shard Map Manager database, create shards, load data, execute queries, and delete shards. From a map management standpoint, it will maintain the global mapping information and maintain your list of range map for your sharded databases. Your data will be distributed across your shards based on the shard key that you choose. Some common examples of a shard key would be something like a customer ID or a tenant ID. All data with the same shard key is distributed to the same shard. This is also the smallest granularity of data movement from one shard to the other. This set of related data is called a shardlet. Keep in mind that all data need not be sharded. In some cases, you might copy an entire table to every shard. Examples would include things like reference data or date dimensions. So let's look at some of the tools and features used to manage multi-tenant systems. Elastic database tools are what we use to manage sharding from the application and to administer shards from the back end. The tools consist of client libraries, the split merge tool, elastic pools, and queries. The elastic database tools simplify data tier development in a sharded environment, especially in environments with many databases. Some of the functionality provided by the elastic database tools include data-dependent routing, which is used by the application to execute typical application queries. When using data-dependent routing, the Shard Map Manager directs your query to the appropriate shard. Shard elasticity, which is used to scale an individual shard up or down. Merge, which is used to merge two underutilized shards into a single shard. Split, which likewise is used to split a single shard into two. And the shard set executor, which is used to execute queries across all shards. This is commonly used to make things like schema changes across all the databases. Elastic database jobs are used to execute T-SQL and maintenance tasks across a group of databases. It provides job execution tracking and auto retry. Target groups can be comprised of individual databases, all databases on a particular server, or all databases in an elastic pool or shard map. Targets can be in different servers, subscriptions, or regions. All right, so next we want to take a look at Elastic Database Jobs. So Elastic Database Jobs are a tool that is designed to help you execute jobs across a number of servers or Azure SQL databases or elastic pools. It does not require an elastic pool to take advantage of an elastic job. Elastic jobs are independent of an elastic pool, but they do integrate well with elastic pools. So in our case here, we have one elastic pool called Pool 1. This is the same elastic pool that we used earlier. We have a new tenant database that we added in the previous demo, and we have the other databases that were included in that elastic pool. So no changes have been made to this elastic pool since the last demo that we did in this presentation. The JobDB database I have pre-created, and this is the job database that will hold the metadata about our job and coordinate the execution of jobs across multiple servers or databases or elastic pools. So what we want to do is we need to now create an elastic job, and you do that in the portal. And we're going to search for the elastic job. Let's see, the elastic job agent shows up. So we'll select that. It's going to ask for a name. I'm just going to call it job agent. And then you see it's going to ask me to select a job database. This is why I pre-created our job database. And your job database can live anywhere. Mine happens to live here. So we'll select that. This job database does not have to be very large. Mine is an S1. That's perfectly fine. It's not going to be under heavy load. So if you do, maybe if you're running lots of jobs simultaneously and lots of updates are happening, you might want to go to S1 or S2, but realistically S0 is probably enough to support most scenarios. So let's go ahead and click create. And this will take a few minutes to execute. and then we should be able to carry on from there. So let's go to our multi-tenant DB location, and I'll click refresh. Now in real life, this is going to take a couple of minutes to deploy. I'm going to edit the video so it's going to seem like it's a lot faster than it really is, but it just takes a minute or two to deploy. Okay, it looks like we're finished, so let's go ahead and click refresh. And there's our job agent. You can see it right here. And if I select our job agent, you'll see that we have a couple of things. One is we have a server name that we are tied to and a job database that we are tied to. Those are the only configuration options we had. You'll also see down below, this is the summary of the executions that you've done inside of this job agent. We haven't had a chance to set anything up yet, so we don't have any executions. If you want to see what jobs are assigned to your job agent, you can select jobs down here from the menu, and you'll see that there's no jobs present currently. So let's go back to the overview. And now what we want to do is we want to jump into SQL Server Management Studio and configure a job to execute across our Elastic pool. Here we are in Management Studio. I've already connected to our logical SQL server in Azure, and you can see the databases that I have under here. I'll click refresh. So let me go ahead and open up Contoso Concert Hall so we can take a look at that. And we'll refresh the list of tables. And you can see right here, we've got some basic tables in here. This is just some demo data. And what we're going to do is we're going to run a query to add a new table to every database in our pool. So the databases that are currently in our pool are Contoso Concert Hall, Dogwood Dojo. We removed Fabricam Jazz Club, and New Tenant is also part of that pool. Now, from a security standpoint, we're logged in with this developer login. And this developer login is mapped to the DBO user in every one of our databases. So this is an admin. In practical terms, you're probably going to use different accounts and credentials for different levels of access. For ease of the demo, I just use the same account. That's an admin account, but you can lock it down a little bit further. You're going to have two credentials that you're going to use. One is used to execute jobs, and the other one is used to refresh job metadata, job status, and that type of thing. So slightly different result sets. The job metadata refresh is pretty lightweight, whereas the other job execution credential, that's the security context you will use when you're executing your jobs. So let's go ahead and do this. First, we need to create a master key for the job database. Now, before I execute this, I do want to point out this needs to be executed from the job database itself. So if I look up in Management Studio to the top left here, you can see that I am actually in master right now. So let's switch to JobDB and let's go execute, and that will complete successfully. And now we've got two credentials that we need to create. One is the execution credential and the other is the metadata credential. We're just going to go ahead and create both of these at the same time. And what this is doing is storing the username and then the secret that goes with it in a credential, in a database scope credential. This will be stored within the JobDB database. So now the next thing we need to do is we need to create a target group. Now your target group can contain, like I said, any number of databases or servers, or if you assign a server, it's going to choose every database on the server. You can also choose an Elastic pool as a target. So what I'm going to do is I'm going to choose an Elastic pool because we have a database on that Elastic in that server that is not part of the pool. That's the Fabricam Jazz Club, which we've removed from our Elastic pool in the last demo. First, let's go ahead and create the target group. And this is just to give us some information. We do need to be in the job database, so I'm going to go ahead and switch to that. That command completed successfully. Then we're going to add a group member to this target group. And this is going to be our Elastic pool. And I execute this real quick, and then I'll talk about what we have here. Here, we're using the credential that's required to refresh the databases in a server defined. we have the server name that the pool belongs to, and then the Elastic pool name that we've defined. If you want to view these groups and the membership in these groups, you can use these system tables to get that. We'll execute that, and you can see the information down here. So you can get the group IDs and things like that for more advanced scripting. So now let's go ahead and create our job. So we're going to add a job for creating a table. We're going to call it create table test. Pretty simple. And we've given it a description of the same. Also, this needs to be in the job database again. Need to switch to JobDB. We'll execute that. So now we have the job. Now we need to add the actual job step. And this is going to be the commands that are going to be executed by the job. And you can have any number of steps. So a couple of things before we execute this. You're going to specify the job name. And you can see that right here. We're also going to have the command, and you'll notice that this command is using the if not exist syntax as well. And this is because you want this script to be idempotent. So if I execute this script twice, it shouldn't fail just because there's already an existing table. So that's what we're checking. Also note that you're putting this whole script in quotes. So if you need to quote something within that, the syntax to escape a quote is another single quote in T-SQL. Pass in the credential name and the target group name as well. So let's execute that. All right, that completed successfully. And all that's left for us to do now is to execute the job. Once I execute this command, this will just start the latest version of the job, whatever the job is, and it'll just blindly go and execute the latest version. If you need to get the execution ID, so if you're going to use it in a script to validate status or anything like that, you can use this query here, and this will execute the job, and then it will return and obtain the job execution ID, which then you can use to do things like check status and that kind of thing. If you wanted to specify a different version of the job, you can use this syntax here, which also has the version appended to the end of it here. We only have one version of the job because we've only created it and we haven't modified it. But if you had multiple versions, say you're working on a new version, but you still want to use the old version at some point, or you create a new version and it fails for some unknown reason and you want to revert back to an old version, you have that ability to do that as well. For our purposes, we're just going to execute the job straight away. So let's go and check on this, and we're going to do that by going through the portal. You could also use T-SQL commands to check for status output by using the execution ID, but let's go ahead and try checking it through the portal. So let's go ahead and refresh this, and you can see here's our job that succeeded. And if we go into our jobs, you can see that we have a job that shows up here in the list of jobs. And this is currently disabled because it's not set to run on a schedule, but we could configure a schedule and have it run on a schedule as well. If we go to target groups, you can see we have our pool group here in the portal. That shows us what we're using there. And if we go to credentials, you can see I have my credentials here as well. The overview shows you your last executions. So you can see that that's showing up here. Pretty straightforward. You'll see a list of the latest 100 job executions. If you need to see more than that, you can use T-SQL to see more than that.